Testing, testing, hello. Hey everybody, this is the Reduction and Oxidation Screencast. We're going to learn one more thing about our single replacement reactions. We're going to keep this one pretty short so you guys can pause and rewind as many times as you need to until this becomes pretty clear for you. So let's get going right away. Let's think of a reaction here. I want to put this zinc bar into this solution of copper 2 chloride. Okay, so this is zinc metal right there. That is in the solid state. And let's say I've got a copper 2 chloride solution, and because it's a solution, I know the state of matter is aqueous. Let's think of what the chemical equation is going to be for this reaction. I know that zinc and copper 2 chloride will react because zinc is higher than copper on the activity series. When zinc replaces copper, copper is knocked out on its own, and zinc chloride is the result. Okay, so now we need to know how to write our complete ionic equation. Remember, the ionic equation, or the only difference between the chemical equation, which we just wrote, and the complete ionic equation is this all the compounds that appear in aqueous states of matter are separated out into their ions. Okay, we're showing dissociation in our reaction. So here we go. Let's leave zinc alone. Let's dissociate copper 2 chloride. So copper by itself is a +2 ion. It is aqueous. There's the chloride ion, but in copper 2 chloride, I can see that there are 2 chloride ions, so I need a 2 in front of this chloride, and that is aqueous. Leave copper alone. It's a solid. Let's show dissociation in zinc chloride. So zinc by itself is a +2 ion. It's aqueous. There are 2 chloride ions, and they are aqueous. Okay, so there's our complete ionic equation, but we need to cancel out what's the same on both sides. All right, on the left side, I can see 2 chlorides, and on the right side, I see 2 chlorides. So if they're the same on the left and right side of the equation, basically that means that nothing changed, nothing happened to chloride. They were just sitting there watching. We call those spectator ions. So let's write the net ionic equation. Okay. There's our net ionic equation, and we need to take a closer look at a few of these substances here. Okay, I want to notice the difference between zinc on the left and right and the difference between copper on the left and right. So if I'm looking at zinc, I see that zinc is like a normal atom over here, but it's an ion over here. Okay, what happened in order for this change to occur? What changed with zinc? Zinc started as a neutral atom on the left and is now a +2 ion on the right. Well, in order for zinc to become a +2 ion, it must have lost 2 electrons. Okay, if it lost 2 electrons, that's like taking away negative charge. So now zinc is more positive on the right. So in this process, in this reaction, the zinc atom is losing 2 electrons. I'm going to write that on this line here. Okay, it lost 2 electrons. Now let's take a closer look at copper. Here's copper on the left, here's copper on the right. Now copper starts out as a +2 ion but ends as a neutral atom. What must have happened in order for this change to have occurred? In order for copper to start as a +2 ion and then become a neutral atom, it's sort of like the exact same thing that we see in zinc but happening in reverse. So copper must be gaining 2 electrons. All right. Think about really what must happen for something to become an ion. If something is becoming a positive ion, it's because it's losing electrons. That's what's happening in zinc. Okay, if you identify that zinc is the thing that's losing electrons, it's easy to identify copper as the thing that's gaining electrons because it's the same thing happening in reverse. Okay. Let's talk about what the special word is for gain and loss of electrons. Let's go to the next page here. We've got these 2 special words. One is oxidation, and one is reduction. Okay, we need to remember that oxidation is the loss of electrons, and the reduction is the gain of electrons. I know that's kind of backwards. Like you want to think that reduction means to lose, but it's sort of backwards in this chemical example. Okay, so oxidation is loss, reduction is gain. Maybe an easy way to remember that for you is to think about the letters here. So oxidation is loss, O-I-L, and reduction is gain, R-I-G, oil rig. Not sure if that'll help you out too much, but maybe it's a good memory device for you. Oxidation is the loss of electrons, reduction is the gain of electrons. So if we go back and look at our equation real fast here, we see that zinc is losing electrons and copper is gaining electrons. Okay? Zinc is losing, copper is gaining. Okay, so if zinc is the element that's losing electrons, we say that zinc is oxidized. And if I could spell oxidized right, that'd be awesome. If we look at copper, we can see that copper is gaining electrons in this equation. So we would say copper is reduced. Okay, so those are our new special words. And back to this equation here, we're really taking a closer look at exactly what is happening in our net ionic equation. That's kind of the whole point of doing this whole process. We spent some time learning how to go from our complete, or how to write our complete ionic, and we really just do that in order to get to our net ionic. Now that we've written our net ionic, we can see what is actually happening in this chemical equation. Okay, that's the kind of thing you'll have to do on your single replacement post-lab quiz, which is on Monday. We already know how to write our chemical equations. Remember that there are several reactions that we saw in our lab. Make sure you know how to write those equations out. We need to know how to write our complete ionic and our net ionic. And now we can take, after watching the screencast, take a closer look at really what's happening in that net ionic equation. Okay, that's it. Thanks, guys.